All right, I'm going to try to pick this up a little before the end of the last video. So this relationship between what's called the recession velocity and the distance is is called Hubble's law. We're going to use the term recession velocity when we talk about the v in the equation, and d is simply the distance in megaparsecs, as you're going to see. Because of the constant. The constant turns out to be Hubble's constant, and it's really just the slope of this graph. That's really where it came from. All right, so here's the equation. Of course, it says the recession velocity equals the Hubble constant times the distance, and so the value that we're going to use is the 70 kilometers per second per megaparsec. So that's the v is equal to h times d. That's Hubble's law, and really what this is a reflection of is the fact that the universe is expanding. Right? This isn't when you look at the graph. When you look at these graphs right here, you think that it has something to do with the velocities of the individual galaxies, but it really doesn't, because if you think about it, galaxies would be just moving randomly throughout the universe. I mean, of course, they're influenced by the gravitation due to other galaxies in their galactic clusters. That's fine, but that would mean that they're moving in all sorts of directions. Certainly, you wouldn't imagine that as the universe as you look out into the universe, you would have every single galaxy moving away from us, and moving away from us in a very ordered way. And so that's really what the problem was initially when Hubble made this discovery, and quickly realized that it is not the motion of any galaxies. It's really this cosmic distance, this galactic distance that allows us to see the expansion of the universe. Essentially, so the universe has been expanding since the Big Bang. When the Big Bang occurred, we'll get a lot more into that in chapter 26. But that's really the cause. And the other thing about this is there's I think it's called table 24.2. We really need to look at that. It's in the e-text. It turns out when the recession the recession velocity comes from what's called the redshift, of course. When you look here, I think we had the picture. So this is the real thing that's going on. Is there's this redshift, and then as you get further and further out into the universe, the redshift gets greater and greater, and the redshift is an indication of velocity. Of course, that's from the Doppler effect. We learned that. But the problem with the Hubble constant, with Hubble's law, it's not really a problem if you understand that you have to take into account relativity, right? When the recession velocity begins to get really, really large, remember it's just because of distance. It's like if you were imagine an ant on the surface of a balloon, and if the ant took a certain amount of time to go from point A to point B, if someone were blowing up the balloon, that ant would take longer to go between point A and point B, because when they took off, it was a certain distance, and then as they were traveling the distance, the balloon expanded. That's the idea of Hubble's law, right? So the problem comes in the fact that when you get out to about 100 megaparsecs or so, the recession velocity starts to approach the speed of light, and so this simple relationship breaks down when you get to distances out to about 100 megaparsecs or so. And so you need that table. I think it's 24.2, and you just use that table because they've already done the calculations using the theory of relativity. So really, all you have to know is what the redshift is, and then you can figure out what the recession velocity is. And the recession velocity will never get above the speed of light. It'll get really close to the speed of light, but it can never be above the speed of light. All right. So that's, again, that was the final step on in our distance ladder. You start bouncing radar off of objects within the solar system. Then you get outside the solar system, and so you use the orbit of the Earth itself as the baseline for a parallax. So stellar parallax, so we can measure the distance to stars this way, because with our telescopes we can measure this. And of course, nowadays we have satellites that have extended this baseline. And so the original 200 parsecs is actually, I think, expanded out to, it's actually pretty far. But you have to use those satellites for particular stars, right? I think we can go out to almost 10,000 parsecs with the old-fashioned stellar parallax, but that's if you're actually looking at a particular star. And I think I had mentioned this before. This is a really important concept, so it does bear repeating. Is that we need to have overlap. There has to be overlap between each of these rungs on the distance ladder, because without a way of verifying it, in fact, there has to be Cepheid variables, right? So the Cepheid variables are this rung up here, but there are Cepheid variables that are close enough to us that we can measure using stellar parallax. And then, of course, there are stars. There are stars that are closer to us that we can do the spectroscopic parallax, and so we can use stellar parallax to verify the values that we get using spectroscopic parallax. And then, of course, again, you keep looking for as much overlap as you can. For example, the Tully-Fisher method, right? That's for spiral galaxies, and that works, really well from about 25 megaparsecs to 200 parsecs out there. But of course, we have galaxies that are closer. In fact, the closest spiral galaxy to the Milky Way, of course, is the Andromeda galaxy, which we can actually measure the Andromeda galaxy, the distance to the Andromeda galaxy, which is in fact what Hubble originally did, using variable stars, using Cepheid variable stars. In fact, that's how he was the first one to ever find Cepheid variables in the Andromeda galaxy, and was the first one to actually realize that it was a galaxy unto itself. That there wasn't just the Milky Way out there in the universe. Anyhow, so if we can use Cepheid variables on close by spiral galaxies such as the Andromeda galaxy, and then we can also use the Tully-Fisher method on those close by galaxies, and that gives us confidence that the more distant galaxies where you can't see Cepheid variables, that this Tully-Fisher method works. All right, so again, overlap. And then, of course, the method of standard candles is the next rung, and so that's using type 1 supernova. That's a white dwarf that accumulates more than 1.4 times the mass of the sun and then blows up. It always blows up with the same luminosity, as the same characteristic curve, and so that we use that to measure distances. And of course, there's overlap between using the type 1 supernova and these other methods. Of course, for example, there's galaxies that are close by, relatively close by, where spiral galaxies, I should say. By the way, there is another method. It's a lot more complex for elliptical galaxies, but it's similar. It was what's it called? Something Faber and Jackson or something like that. Anyhow, It's much more complicated than Tully-Fisher, and that's for elliptical galaxies. Right, and so the last one is, of course, the Hubble's law, and so that's the final rung on the distance ladder. But we're always trying to find more ways to measure distances. All right, now we're going to turn our attention to what are called active galaxies. Let's keep in mind our galaxy, the Milky Way, Andromeda. Most of the galaxies in the nearby neighborhood of galaxies are what we would call normal galaxies. So a normal galaxy shows a characteristic black body curve, right? So this black body curve, for example, has a peak, a peak wavelength. It's usually in the visible part of the spectrum, but it doesn't have to be. But the fact that it has this curve, all right? An active galaxy, for example, has what we would call a non-stellar non-stellar radiation. So it has basically like this line that it's showing that this would indicate an active galaxy. Active galaxies are always emitting more energy than other normal type galaxies. And most galaxies are normal, but these active galaxies, we find some. And so they're putting out all sorts of. We're gonna actually. There's many different types. There's in fact a whole zoo of active galaxies, and so you could just spend your entire life studying active galaxies. But what we generally do is we try to narrow it down to three basic types. All right, the three basic types are Seyfert galaxies, which happen to be active spiral galaxies, radio galaxies. And the other one would be what are called quasars, which is actually related. Quasars are related to the other galaxies. We'll get into the story of quasars a little bit later. So we're going to study each of these, and just keep in mind they have this non-stellar radiation that's coming from them, and it's more energy than can be accounted for by all the stars in that particular galaxy. And so there's some engine that is creating all this energy, and we're going to investigate what that is. All right, so here we go. So this is again what we call non-stellar. Some books call it non-thermal radiation, right? Because thermal radiation gives this black body curve. All right, anyhow, non-stellar or thermal or non-thermal radiation is another term for it. So these things are producing incredible amounts of energy, and some of them, in fact, and not all of them, but some of them actually have what they call starburst. So there's incredible star formation taking place, and we'll look into that a little bit and why we think that is occurring. All right, so again, we're gonna focus on the three different types: Seyfert, radio galaxies, and quasars. All right, so here is an example of this is just a general active galaxy right now. So they look just like other galaxies. You wouldn't really even notice this unless you're looking. In fact, most of the energy is not in the visible part of the spectrum. Right, so it turns out that the galaxies look just like the regular galaxies. All right, so again, okay, here we go. Here are the three general types. Again, there are subdivisions of all these, but we're just going to look at the three general types. The Seyfert, which again are always spiral galaxies, radio galaxies, and quasars. All right, so all right, and this is a key thing, is that they tend to be thousands of times more luminous than the average galaxy. For example, you have stars that are galaxies, active galaxies that I think have luminosities approaching like 10 to the 37th watts, were 10 to the 40th watts. So, and that's